The Lockheed Martin F-22 Raptor is a fifth-generation, single-seat, twin-engine, all-weather stealth tactical fighter aircraft developed for the United States Air Force, U.S. Air Force. The result of the U.S. Air Force's Advanced Tactical Fighter program, the aircraft was designed primarily as an air superiority fighter, but also has ground attack, electronic warfare, and signal intelligence capabilities. The prime contractor, Lockheed Martin, built most of the F-22's airframe and weapons systems and conducted final assembly, while Boeing provided the wings, aft fuselage, avionics integration, and training systems. The aircraft was variously designated F-22 and F/A-22 before it formally entered service in December 2005 as the F-22A. After a protracted development and despite operational issues, the U.S. Air Force considers the F-22 critical to its tactical air power, and says that the aircraft is unmatched by any known or projected fighter. The Raptor's combination of stealth, aerodynamic performance, and situational awareness gives the aircraft unprecedented air combat capabilities. The high cost of the aircraft, a lack of clear air-to-air missions due to delays in Russian and Chinese fighter programs, a ban on exports, and development of the more versatile F-35 led to the end of F-22 production. A final procurement tally of 187 operational production aircraft was established in 2009, and the last F-22 was delivered to the U.S. Air Force in 2012. Development. Origins. In 1981, the U.S. Air Force developed a requirement for an Advanced Tactical Fighter, ATF, as a new air superiority fighter to replace the F-15 Eagle and F-16 Fighting Falcon. Code-named Senior Sky, this program was influenced by the emerging worldwide threats, including development and proliferation of Soviet Su-27 flanker and MiG-29 Fulcrum-class fighter aircraft. It would take advantage of the new technologies in fighter design on the horizon, including composite materials, lightweight alloys, advanced flight control systems, more powerful propulsion systems, and stealth technology. The Request for Proposals, RFP, was issued in July 1986 and two contractor teams, Lockheed/Boeing/General Dynamics and Northrop/McDonnell Douglas, were selected on October 31, 1986 to undertake a 50-month demonstration phase, culminating in the flight test of two technology demonstrator prototypes, the YF-22 and the YF-23. The program was managed by the Advanced Tactical Fighter Systems Program Office, ATF-SPO, located at Wright-Patterson Air Force Base. Each design team produced two prototype air vehicles, one for each of the two engine options. The Lockheed-led team employed thrust vectoring nozzles on YF-22 for enhanced maneuverability in dogfights. The ATF's increasing weight and cost drove out certain requirements during development. Side-looking radars were deleted, and the dedicated infrared search and track, IRST, system was downgraded from multicolor to single color and then deleted as well. However, space and cooling provisions were retained to allow for future addition of these components. The ejection seat requirement was downgraded from a fresh design to the existing McDonnell Douglas ACES II. After the flight test demonstration and validation of the prototypes, on April 23, 1991, Secretary of the U.S. Air Force Donald Rice announced the YF-22 as the winner of the ATF competition. The YF-23 design was considered stealthier and faster, while the YF-22 was more maneuverable. The aviation press speculated that the YF-22 was also more adaptable to the U.S. Navy's Navalized Advanced Tactical Fighter, NATF, but by 1992, the Navy had abandoned NATF. Production and procurement. Prime contractor Lockheed Martin Aeronautics manufactured the majority of the airframe and performed final assembly at Dobbins Air Reserve Base in Marietta, Georgia. Program partner Boeing Defense, Space and Security provided additional airframe components as well as avionics integration and training systems. F-22 production was split up over many subcontractors across 46 states to increase congressional support, though this production split may have contributed to increased costs and delays. Many capabilities were deferred to post-service upgrades, reducing the initial cost but increasing total program cost. Production supported over 1,000 subcontractors and suppliers and up to 95,000 jobs. The F-22 had several design changes from the YF-22. The swept-back angle of the leading edge was decreased from 48 degrees to 42 degrees, while the vertical stabilizers were shifted rearward and decreased in area by 20%. To improve pilot visibility, the canopy was moved forward 7 inches, 18 centimeters, and the engine intakes moved rearward 14 inches, 36 centimeters. The shapes of the wing and stabilator trailing edges were refined to improve aerodynamics, strength, and stealth characteristics. Increasing weight during development caused slight reductions in range and aerodynamic performance. The first F-22, an engineering and manufacturing development (EMD) aircraft named Raptor 4001, was unveiled at Marietta, Georgia, on April 9, 1997, and first flew on September 7, 1997. In 2006, the Raptor's development team, composed of over 1,000 contractors and the U.S. Air Force, won the Collier Trophy, American aviation's most prestigious award. The F-22 was in production for 15 years, at a rate of roughly 2 per month during peak production. The U.S. Air Force originally envisioned ordering 750 ATFs at a cost of $26.2 billion, with production beginning in 1994. The 1990 Major Aircraft Review led by Secretary of Defense Dick Cheney reduced this to 648 aircraft beginning in 1996. By 1997, funding instability had further cut the total to 339, which was again reduced to 277 F-22s by 2003. In 2004, the Department of Defense, DoD, further reduced this to 183 operational aircraft, despite the U.S. Air Force's preference for 381. In 2006, a multi-year procurement plan was implemented to save $15 billion but raise each aircraft's cost. That year the program's total cost was projected to be $62 billion for 183 F-22s distributed to 7 combat squadrons. In 2007, Lockheed Martin received a $7.3 billion contract to increase the order to 183 production F-22s and extend manufacturing through 2011. In April 2006, the Government Accountability Office, GAO, assessed the F-22's cost to be $361 million per aircraft, with $28 billion invested in development and testing. The unit procurement cost was estimated at $178 million in 2006, based on a production run of 181 aircraft. It was estimated by the end of production, $34 billion will have been spent on procurement, resulting in a total program cost of $62 billion, around $339 million per aircraft. The incremental cost for an additional F-22 was estimated at about $138 million in 2009. The GAO stated the estimated cost was $412 million per aircraft in 2012. Ban on exports. The F-22 cannot be exported under American federal law to protect its stealth technology and other high-tech features. Customers for U.S. fighters are acquiring earlier designs such as the F-15 Eagle and F-16 Fighting Falcon or the newer F-35 Lightning II, which contains technology from the F-22 but was designed to be cheaper, more flexible, and available for export. In September 2006, Congress upheld the ban on foreign F-22 sales. Despite the ban, the 2010 Defense Authorization Bill included provisions requiring the DoD to prepare a report on the costs and feasibility for an F-22 export variant, and another report on the effect of F-22 export sales on U.S. aerospace industry. Some Australian politicians and defense commentators proposed that Australia should attempt to purchase F-22s instead of the planned F-35s, citing the F-22's known capabilities and F-35's delays and developmental uncertainties. However, the Royal Australian Air Force, RAF, determined that the F-22 was unable to perform the F-35's strike and close air support roles. The Japanese government also showed interest in the F-22 for its replacement fighter program. The Japan Air Self-Defense Force, JASTF, would reportedly require fewer fighters for its mission if it obtained the F-22, thus reducing engineering and staffing costs. However, in 2009 it was reported that acquiring the F-22 would require increases to the defense budget beyond the historical 1% of GDP. With the end of F-22 production, Japan chose the F-35 in December 2011. Israel also expressed interest, but eventually chose the F-35 because of the F-22's price and unavailability. Production termination. Throughout the 2000s, the need for F-22s was debated due to rising costs and the lack of relevant adversaries. In 2006, Comptroller General of the United States David Walker found that the DoD has not demonstrated the need for more investment in the F-22, and further opposition to the program was expressed by Secretary of Defense Donald Rumsfeld, Deputy Secretary of Defense Gordon R. England, Senator John McCain, and Chairman of U.S. Senate Committee on Armed Services Senator John Warner. The F-22 program lost influential supporters in 2008 after the forced resignations of Secretary of the Air Force Michael Wynne and the Chief of Staff of the Air Force General T. Michael Mosley. Nevertheless, in 2008, Congress passed a defense spending bill funding the F-22's continued production and the Pentagon released $50 million of the $140 million for 4 additional aircraft, raising the total orders for production aircraft to 187 and leaving the program in the hands of the next administration. In November 2008, Secretary of Defense Robert Gates stated that the Raptor was not relevant in post-Cold War conflicts such as in Iraq and Afghanistan, and in April 2009, under the new Obama administration, he called for ending F-22 production in fiscal year FY 2011, leaving the U.S. Air Force with 187 production aircraft. In July, General James Cartwright, Vice Chairman of the Joint Chiefs of Staff, stated to the Senate Committee on Armed Services his reasons for supporting termination of F-22 production. They included shifting resources to the multi-role F-35 to allow proliferation of fifth-generation fighters for 3 service branches and preserving the F/A-18 production line to maintain the military's electronic warfare (EW) capabilities in the Boeing EA-18G Growler. Issues with the F-22's reliability and availability also raised concerns. After President Obama threatened to veto further production, the Senate voted in July 2009 in favor of ending production and the House subsequently agreed to abide by the 187 production aircraft cap. Gates stated that the decision was taken in light of the F-35's capabilities, and in 2010, he set the F-22 requirement to 187 aircraft by lowering the number of major regional conflict preparations from 2 to 1. In 2010, U.S. Air Force initiated a study to determine the costs of retaining F-22 tooling for a future Service Life Extension Program, SLEP. A RAND Corporation paper from this study estimated that restarting production and building an additional 75 F-22s would cost $17 billion, resulting in $227 million per aircraft, or $54 million higher than the flyaway cost. Lockheed Martin stated that restarting the production line itself would cost about $200 million. Production tooling will be documented in illustrated electronic manuals stored at the Sierra Army Depot. Retained tooling will produce additional components. Due to the limited production run, there are no reserve aircraft, leading to considerable care during maintenance. Later attempts to retrieve this tooling found that the containers were empty. The Pentagon cannot continue with business as usual when it comes to the F-22 or any other program in excess of our needs. Secretary of Defense Robert Gates, speaking on the cancellation. Russian and Chinese fighter developments have fueled concern, and in 2009, General John Corley, head of Air Combat Command, stated that a fleet of 187 F-22s would be inadequate, but Secretary Gates dismissed this concern. In 2011, Gates explained that Chinese fifth-generation fighter developments had been accounted for when the number of F-22s was set, and that the U.S. would have a considerable advantage in stealth aircraft in 2025, even with F-35 delays. In December 2011, the 195th and final F-22 was completed out of 8 test, EMD engineering, manufacturing, and development, and 187 operational aircraft produced. The aircraft was delivered to the U.S. Air Force on May 2, 2012. In April 2016, the HASC Tactical Air and Land Forces Subcommittee proposed legislation that would direct the Air Force to conduct a comprehensive assessment and study of the costs associated with resuming production of F-22 aircraft. Defense Secretary Robert Gates had production halted at 187 F-22s, at a cost of $67 billion, to direct funds for ongoing irregular warfare operations in Iraq and Afghanistan. Since then, lawmakers and the Pentagon noted that air warfare systems of Russia and China were catching up to U.S. air superiority capabilities. Previous estimates of restarting production placed figures at around $2 billion, including $300–500 million in non-recurring startup costs, with an estimated unit cost of $233 million for a production run of 75 aircraft over 5 years. Lockheed has proposed upgrading the 36 early training model Block 20 Raptors into combat-coded Block 30 35th versions as a way to increase numbers available for deployment. On June 9, 2017, the Air Force submitted their report to Congress stating they had no plans to restart the F-22 production line due to economic and operational issues. It estimated it would cost approximately $50 billion to procure 194 additional F-22s, at a cost of $206–216 million per aircraft, including approximately $9.9 billion for non-recurring startup costs and $40.4 billion for aircraft procurement costs. Upgrades. The first combat-capable Block 3.0 aircraft first flew in 2001. Increment 2, the first F-22 upgrade program, was implemented in 2005 and enables the aircraft to employ Joint Direct Attack Munitions, JDAM. Increment 3.1 provides improved ground attack capability through synthetic aperture radar mapping and radio emitter direction finding, electronic attack, and the GBU-39 Small Diameter Bomb, SDB. Testing began in 2009 and the first upgraded aircraft was delivered in 2012. Increment 3.2 is a two-part upgrade process. 3.2a focuses on electronic warfare, communications, and identification, while 3.2b will allow the F-22 to fully exploit the AIM-9X and AIM-120D missiles. The subsequent Increment 3.3 may include the adoption of an open avionics platform and air traffic control updates. Upgrades due in 2015 will allow the F-22 to employ the AIM-9X and have full Link 16 reception and transmission capability. The F-22 fleet is planned to have 36 Block 20 training and 149 Block 30 35th combat aircraft by 2016. The Increment 3.2b upgrade planned for 2018 will include a new stores management system to show the correct symbols for the AIM-9X Sidewinder and AIM-120D AMRAAM with improved control of them. In 2017, the U.S. Air Force is defining requirements for next-generation sensors for the F-22, which involves designing new hardware and antennas. Subsequent upgrades are also focusing on an open avionics platform to enable faster future upgrades. To enable two-way communication with other platforms, the F-22 can use the Battlefield Airborne Communications Node, BACN, as a gateway. The originally planned MADL integration was cut due to the lack of system maturity. In 2014, Lockheed Martin and Northrop Grumman were competing to connect the F-22 with other platforms while maintaining stealth. Other upgrades being developed include infrared search and track functionality for the AAR-56 missile launch detector, MLD, and integration of a helmet-mounted queuing system, HMCS, to enable off-boresight missile launches by 2020. Until the F-22 gains a helmet-mounted system, it will use the AIM-9XS helmetless high off-boresight (HOBS) capabilities. In March 2010, the U.S. Air Force accelerated software portions of 3.2 to be completed in FY 2013. In January 2011, the U.S. Air Force opened the Raptor Enhancement, Development, and Integration (REDI) contract to bidders, with a $16 billion budget. In November 2011, Lockheed Martin's upgrade contract ceiling was raised to $7.4 billion. Nearly $2 billion was allocated for structural repairs and to achieve fleet availability rate of 70.6% by 2015. However, only 63% was achieved. Some F-35 technology, such as more durable stealth coatings, have been applied to the F-22. By 2012, the update schedule had slipped 7 years due to instability in requirements and funding. In 2014, the U.S. Air Force moved to cut upgrade funding. In 2012, the F-22 was upgraded with a backup oxygen system, software upgrades and oxygen sensors to address the frequent oxygen deprivation issues and normalize operations. In 2013, the faulty flight vest valves were replaced and altitude restrictions lifted. Distance restrictions will be lifted once a backup oxygen system is installed. In April 2014, the U.S. Air Force stated in congressional testimony that installation of automatic backup oxygen systems on the F-22 fleet would be completed within 12 months. The F-22 was designed for a lifespan of 30 years and 8,000 flight hours, with a $100 million structures retrofit program. Investigations are being made for upgrades to extend their useful lives further. In the long term, the F-22 is expected to be superseded by a sixth-generation jet fighter to be fielded in the 2030s. Design Overview. The F-22 Raptor is a fifth-generation fighter that is considered fourth-generation in stealth aircraft technology by the U.S. Air Force. It is the first operational aircraft to combine supercruise, supermaneuverability, stealth, and sensor fusion in a single weapons platform. The Raptor has clipped delta wings with a reverse sweep on the rear, 4 empennage surfaces, and a retractable tricycle landing gear. Flight control surfaces include leading-edge flaps, flaperons, ailerons, rudders on the canted vertical stabilizers, and all moving horizontal tails. These surfaces also serve as speed brakes. The aircraft's dual Pratt & Whitney F119 PW100 afterburning turbofan engines are closely spaced and incorporate 2D pitch axis thrust vectoring nozzles with a range of plus or minus 20 degrees. Each engine has maximum thrust in the 35,000 lbf, 156 knots, class. The F-22's thrust-to-weight ratio in typical combat configuration is nearly at unity in maximum military power and 1.25 in full afterburner. Maximum speed without external stores is estimated to be Mach 1.82 during supercruise and greater than Mach 2 with afterburners. The F-22 is among only a few aircraft that can supercruise, or sustain supersonic flight without using fuel-inefficient afterburners. It can intercept targets which subsonic aircraft would lack the speed to pursue and an afterburner-dependent aircraft would lack the fuel to reach. The Raptor's high operating altitude is also a significant tactical advantage over prior fighters. The use of internal weapons base permits the aircraft to maintain comparatively higher performance over most other combat-configured fighters due to a lack of aerodynamic drag from external stores. The F-22's structure contains a significant amount of high-strength materials to withstand stress and heat of sustained supersonic flight. Respectively, titanium alloys and composites comprise 39% and 24% of the aircraft's structural weight. The F-22 is highly maneuverable at both supersonic and subsonic speeds. Computerized flight control system and full authority digital engine control, FADEC, make the aircraft highly departure-resistant and controllable. The Raptor's relaxed stability and powerful thrust vectoring engines enable the aircraft to turn tightly and perform very high alpha, angle of attack, maneuvers such as the Herbst maneuver, J-turn, and Pugachev's Cobra. The aircraft is also capable of maintaining over 60 degrees alpha while having some roll control. The Raptor's aerodynamic performance, sensor fusion, and stealth work together for increased effectiveness. Altitude, speed, and advanced active and passive sensors allow the aircraft to spot targets at considerable ranges and increase weapons range. Altitude and speed also complement stealth's ability to increase the aircraft's survivability against ground defenses such as surface-to-air missiles. Avionics. Key avionics include B Systems EINS/ALR-94 Radar Warning Receiver, RWR, Lockheed Martin AAR-56 Infrared and Ultraviolet Missile Launch Detector, MLD, and Northrop Grumman APG-77 Active Electronically Scanned Array, AESA, radar. The MLD features 6 sensors to provide full spherical infrared coverage. The RWR is a passive radar detector with more than 30 antennas blended into the wings and fuselage for all-round coverage. Tom Burbage, former F-22 program head at Lockheed Martin, described it as the most technically complex piece of equipment on the aircraft. The range of the RWR, 250 plus nmi, exceeds the radars, and can cue radar emissions to be confined to a narrow beam, down to 2 degrees by 2 degrees in azimuth and elevation, to increase stealth. Depending on the detected threat, the defensive systems can prompt the pilot to release countermeasures such as flares or chaff. According to Bill Sweetman, experts had said the ALR-94 can be used as a passive detection system capable of searching targets and providing enough information for a radar lock-on. The APG-77 radar features a low observable, active aperture, electronically scanned array that can track multiple targets under any weather conditions. Radar emissions can also be focused to overload enemy sensors as an electronic attack capability. The radar changes frequencies more than 1,000 times per second to lower interception probability and has an estimated range of 125-150 mi, 201-241 km, against a 11 SQ Fort, 1 square meter, target. F-22s from Lot 5 and on are equipped with the APG-77V1, which provides full air-to-ground functionality, high-resolution synthetic aperture radar mapping, ground-moving target indication and track, GMTI/GMTT, automatic cueing and recognition, combat identification, and many other advanced features. The APG-77V1 with newer GAAS modules provides a range of 250 miles, 400 kilometers, or more. This is believed to be possible due to the use of more narrow beams. Radar information is processed by 2 Raytheon Common Integrated Processor, CIPs, each capable of processing up to 10.5 billion instructions per second. In a process known as sensor fusion, data from the radar, other sensors, and external systems is filtered and combined by the CIP into a common view, reducing pilot workload. However, upgrading the aircraft's avionics was reportedly very challenging due to their highly integrated nature. The F-22's ability to operate close to the battlefield gives the aircraft threat detection and identification capability comparative with the RC-135 rivet joint, and the ability to function as a mini-AWACS, though the radar is less powerful than those of dedicated platforms. The F-22 can designate targets for allies, and determine whether 2 friendly aircraft are targeting the same aircraft. This radar system can sometimes identify targets many times quicker than the AWACS. The IEEE 1394B bus developed for the F-22 was derived from the commercial IEEE 1394 Firewire bus system. In 2007, the F-22's radar was tested as a wireless data transceiver, transmitting data at 548 megabits per second and receiving at gigabit speed, far faster than the Link 16 system. The F-22's software has some 1.7 million lines of code, the majority involving processing radar data. Former Secretary of the U.S. Air Force Michael Wynne blamed the use of the DoD's ADA for cost overruns and delays on many military projects, including the F-22. Cyber attacks on subcontractors have reportedly raised doubts about the security of the F-22's systems and combat effectiveness. In 2009, former Navy Secretary John Lehman considered the F-22 to be safe from cyber attack, citing the age of its IBM software. Cockpit. The F-22 has a glass cockpit with all digital flight instruments. The monochrome head-up display offers a wide field of view and serves as a primary flight instrument, Information is also displayed upon 6-color liquid crystal display, LCD, panels. The primary flight controls are a force-sensitive side stick controller and a pair of throttles. The U.S. Air Force initially wanted to implement direct voice input, DVI, controls, but this was judged to be too technically risky and was abandoned. The canopy's dimensions are approximately 140 inches long, 45 inches wide, and 27 inches tall, 355 cm x 115 cm x 69 cm, and weighs 360 pounds. The F-22 has integrated radio functionality. The signal processing systems are virtualized rather than as a separate hardware module. There have been several reports on the F-22's inability to communicate with other aircraft, and funding cuts have affected the integration of the Multi-Function Advanced Data Link, MADL. Voice communication is possible, but not data transfer. The Integrated Control Panel, ICP, is a keypad system for entering communications, navigation, and autopilot data. 2.3 in x 4 in, 7.6 cm x 10.2 cm. Upfront displays located around the ICP are used to display integrated caution advisory/warning data, communications, navigation, and identification, CNI, data, and also serve as the standby flight instrumentation group and fuel quantity indicator. The standby flight group displays an artificial horizon, for basic instrument meteorological conditions. The 8 in x 8 in, 20 cm x 20 cm, primary multifunction display, PMFD, is located under the ICP, and is used for navigation and situation assessment. 6.25 in x 6.25 in, 15.9 cm x 15.9 cm, secondary multifunction displays are located around the PMFD for tactical information and stores management. The ejection seat is a version of the ACES-2, Advanced Concept Ejection Seat, commonly used in U.S. Air Force aircraft, with a center-mounted ejection control. The F-22 has a complex life support system, which includes the onboard oxygen generation system, OBUGs, protective pilot garments, and a breathing regulator/anti-G, brag, valve controlling flow and pressure to the pilot's mask and garments. The pilot garments were developed under the Advanced Technology Anti-G Suit, ADUGS, project and are to protect against chemical/biological hazards and cold water immersion, counter G forces and low pressure at high altitudes, and provide thermal relief. Suspicions regarding the performance of the OBUGs and life support equipment have been raised by several mishaps, including a fatal crash. Armament. The Raptor has 3 internal weapons bays, a large bay on the bottom of the fuselage, and 2 smaller bays on the sides of the fuselage, aft of the engine intakes. The main bay can accommodate 6 LAU-142/A launchers for beyond visual range missiles, and each side bay has an LAU-141/A launcher for short-range missiles. 4 of the launchers in the main bay can be replaced with 2 bomb racks that can each carry 1,000 pounds, 450 kilograms, or 4 250 pounds, 110 kilograms, bombs. Carrying armaments internally maintains the aircraft's stealth and minimizes additional drag. Missile launches require the bay doors to be open for less than a second, during which hydraulic arms push missiles clear of the aircraft. This is to reduce vulnerability to detection and to deploy missiles during high-speed flight. The F-22 can also carry air-to-surface weapons such as bombs with Joint Direct Attack Munition, JDAM, guidance, and the small-diameter bomb, but cannot self-designate for laser-guided weapons. Internal air-to-surface ordnance is limited to 2,000 pounds, 910 kilograms. An internally mounted M61A2 Vulcan 20 mm rotary cannon is embedded in the aircraft's right wing root with the muzzle covered by a retractable door to maintain stealth. The radar projection of the cannon fire's path is displayed on the pilot's head-up display. The F-22's high cruise speed and altitude increase the effective ranges of its munitions, with the aircraft having 50% greater employment range for the AIM-120 AMRAAM than prior platforms. While specifics are classified, it is expected that JDAMs employed by F-22s will have twice or more the effective range of legacy platforms. In testing, an F-22 dropped a GBU-32 JDAM from 50,000 feet, 15,000 m, while cruising at Mach 1.5, striking a moving target 24 miles, 39 kilometers, away. While the F-22 typically carries weapons internally, the wings include 4 hardpoints, each rated to handle 5,000 pounds, 2,300 kilograms. Each hardpoint can accommodate a pylon that can carry a detachable 600-gallon, 2,270 L, external fuel tank or a launcher holding 2 air-to-air missiles. The 2 inboard hardpoints are plumbed for external fuel tanks. The use of external stores degrades the aircraft's stealth and kinematic performance. After releasing stores, the external attachments can be jettisoned to restore those characteristics. A stealthy ordnance pod and pylon was being developed to carry additional weapons in the mid-2000s. Stealth. The F-22 was designed to be highly difficult to detect and track by radar. Measures to reduce radar cross-section include airframe shaping such as alignment of edges, fixed geometry serpentine inlets that prevent line of sight of the engine faces from any exterior view, use of radar-absorbent material, RAM, and attention to detail such as hinges and pilot helmets that could provide a radar return. The F-22 was also designed to have decreased radio emissions, infrared signature, and acoustic signature as well as reduced visibility to the naked eye. The aircraft's flat-thrust vectoring nozzle reduces infrared emissions to mitigate the threat of infrared homing, heat-seeking, surface-to-air or air-to-air missiles. Additional MEA.
Please subscribe and thanks for watching.